Dear viewers, in the previous lectures on linked list, we have discussed the concept of singular linked list, doubly linked list, circular linked list. Here, we are going to discuss the application of linked list. That is, we are going to discuss the representation of stack and queue data structures using linked list. Also, we will discuss the insertion and deletion operations on stack and queue data structures. So, linked list representation of stack. Let us proceed our discussion to representation of stack using linked list. As all of you know, stack is a linear data structure which follow the property last in first out. This means the last inserted element will be the first to be removed. Because of this nature, stack has only one end indicated by the variable top. Top takes care of element present at the top of the stack. Because stack is restricted kind of data structure, so only two operations can be applied to stack, which are insertion, usually termed as push, and deletion, usually termed as pop. No other operation like traversal, searching can be performed, otherwise stack would have lost the property of last in first out. Two conditions are checked while push and pop operation on the stack. One is overflow condition, which means if stack is full, that is there is no space in the stack and we want to push an element, then that element cannot be inserted and we say that overflow condition occurs. Similarly, if the stack is empty and we try to remove an element, then no element can be removed as stack is empty, and then we say underflow condition has occurred. We have already discussed the implementation of stack using array data structure. Arrays put up some limitations when used to implement stack. One of the limitation is static nature of array. This means when array is used to implement stack, the maximum size of stack must be defined before execution of program starts. This is the biggest disadvantage as there may be the overflow when at a moment number of elements becomes more than space allocated to stack. In case to eliminate or reduce the overflows, if large size of array is declared, then there may be the wastage of memory because it may be the case that at most of the time the number of elements in stack is very small. By implementing the stack using linked list, there is no need to know in advance about the maximum size of the stack. Linked list representation of stack allows it to grow or shrink without any prior fixed limit. Of course, this is because of the dynamic nature of linked list. Look at the diagram. Let us see how a stack data structure can be represented using linked list. This is the linked list representation of a stack having 4 elements. One-way linked list is used to represent the elements of the stack. The topmost element is at the beginning of the list. Here the topmost element is 80 and the oldest element is at the end of the list. Here the oldest element is 50. The first element of linked list here is represented by the pointer variable top. Let us discuss the push and pop operations on stack using linked list. Push operation. As you all are aware of, push operation is the insertion of an element at the top of the stack. In case we are using linked list to represent the stack, the push operation can be performed by inserting an element at the beginning of the linked list. While pushing an element, overflow condition must be checked. Here, the overflow condition occurs when stack is full and we are trying to insert an element into it. In case of linked list, overflow condition will occur when the space required to insert an element is not available, which rarely happens. Here is the algorithm depicting the push operation on stack, where the element data is inserted into the stack using linked list. A stack pointer variable top points to the topmost element or node of the stack. This algorithm inserts a new element data into the stack represented by the linked list with a stack pointer variable top pointing to topmost element of the stack. The first step is to allocate memory to a node new. In step 2, the node is prepared for insertion, that is, the desired element is put into the info part of this node. In step 3 and 4, the node new is inserted at the beginning of the linked list. That is, the next part of node new points to node 80 and the stack pointer variable top points to newly inserted node new. This algorithm insert one element into the stack. To insert more than one element, the algorithm is required to be modified. Pop operation. Let us discuss the pop operation on stack data structure. Pop operation is the deletion of an element from the stack. As stack is last in first out data structure, so deletion of an element from stack is restricted at one end only. So, the pop operation can be performed by deleting an element at the beginning of the linked list. While performing pop operation, underflow condition must be checked. Here, the underflow condition occurs when the stack is empty and we try to delete an element from the stack. Here is an algorithm depicting the pop operation on the stack, where the first element or node pointed by stack top variable top is deleted. The step 1 of the algorithm checks the underflow condition. This means if stack pointer variable top is null, it means stack is empty and there is no node present. So, the underflow condition occurs and we exit from the program. In second step, the element in the first node is stored in a variable data for its future usability. Here, the element 80 is stored in variable data. In step 3, the address of first node is stored in a variable temp. This is because at the end, memory held by this node will be deallocated. In step 4, the stack pointer variable top is set to address of second node. Here the stack pointer variable top will point to node 70 as shown here. In step 6, the node 80 whose address is in variable temp is deallocated and memory held by this node is freed. Linked list representation of queue. Let us proceed our discussion to representation of queue using linked list. Queue is a linear data structure which follows the property first in, first out or first come, first serve. This means first inserted element will be the first to be removed. Queue has two ends, one is front, other is rear. Front variable indicate the oldest element inserted into the queue and the rear variable indicates the latest element inserted into the queue. Because Q is a restricted kind of data structure, so only two operations can be applied to the Q, which are insertion and deletion. Insertion operation takes place at rear end and deletion operation takes place at front end. Two conditions are checked while insertion and deletion operation on the Q. One is overflow condition, which means if Q is full, that is, there is no space in the Q and we want to insert an element, then that element cannot be inserted and we say overflow occurs. Similarly, if Q is empty and we want to remove an element, then no element can be removed as Q is already empty and we say underflow condition occurs. By implementing the Q using linked list, there is no need to know in advance about the maximum size of the Q. Linked list representation of Q allows it to grow or shrink without any prior fixed limit. Of course, this is because of dynamic nature of linked list. Look at the diagram. Let us see how a Q data structure can be represented using linked list. In this linked list representation of Q, there are 4 nodes. A one-way linked list is used to represent the elements of the Q, but with a small difference. Here, in case of Q, the address of last node is also stored in a pointer variable known as rear. As shown in this figure, the front variable holds the address of node A, which is the first node of the Q. The pointer variable rear holds the address of node D, which is the last node of the Q. Insertion of new node will take place at rear end, that is after node D. Only node A can be deleted from this Q as node A is at the front of the Q. Let us discuss the insertion of a new element into the Q. As discussed, insertion of new element takes place at the rear end of the Q. Before insertion of new element, the overflow condition must be checked. That is, if Q is already full and we want to insert a new element, then it will be an overflow condition as it is not possible to insert the new node in a full Q. Below is the diagram along with algorithm for insertion of an element E into the Q. The element E is inserted at the rear end of the list. Here in this algorithm, first of all, memory is allocated to a node new. This node is prepared for insertion into the Q. As this node is to be inserted at the rear end, so this node is going to be the last node. Therefore, next part of node new is null and the info part of node new will be E as the element to be inserted is E. Two cases arise while inserting this node new. First, if the linked list is empty, in this case both the front and rear variables will be null. So, after insertion of node new, both variables front and rear will be set to the address of newly inserted node new as shown here. Secondly, if the linked list is not empty, then the node new will be inserted at the rear end by setting the next part of last node to address of node new. Here, note that the address of last node is directly available in variable rear and therefore, we need not to traverse the list to reach at the last node. After the node new is inserted, the variable rear is set to address of newly inserted node as shown in the diagram. Deletion. Let us discuss the deletion operation on queue data structure. As the queue is first in first out data structure, so deletion of an element from the queue is restricted at the front end only. This means deletion of an element from the queue will be performed at the beginning of the linked list. While deleting an element from the queue, underflow condition must be checked. Here the underflow condition occurs when queue is empty and we try to delete an element from the queue. Here is the algorithm depicting the deletion operation on queue. The element at the front end of the queue is deleted. Step 1 of the algorithm checks the underflow condition. This means if the pointer variable front is null, that is if queue is empty, then underflow condition occurs and we exit from the program. In the second step, the element in the first node is stored in a variable data for its future usability. Here, the element of first node is A, which is stored in variable data. In step 3, the address of first node is stored in a variable temp. This is because at the end, the memory held by this node will be deallocated. At this stage, two conditions occur. First, if the queue has only one node, then after deletion of this node, the queue will become empty. So, the variables front and rear will become null as shown in the figure. Secondly, if queue has more than one element, then the second node of the queue will become the first node. Now, front will point to the second node. At the end, the deleted node temp is deallocated and memory held by variable temp is freed. To summarize, we have discussed the linked list representation of stack and queue data structure. The only two operations, insertion and deletion, possible on stack and queue data structures using linked list were also discussed. Hope you have enjoyed this program. So, thank you for watching this program.